Good morning. We will start session 3 on chapter magnetic effects of electric current. So we completed the first part, that is with respect to magnetic effect of electric current, then how the conductor what is magnetized, or we can say how a conductor creates a magnetic field when electric current is passed through it, and on basis of Fleming's left hand rule, or we also call that as a motor rule, we understood how an electric motor works. I had also sent you all a link, animated video, to give you a clear picture how a motor actually works. There you could see the mechanism, including few explanation was also given to same as how I explained. Along with that, it also showed you how the coil rotates, right? So you understood the direction, motion of the conductor. What does Fleming's left hand tell us that? So forefinger indicates magnetic field. Center finger C, where I used indicates current, and main finger, that is thumb finger, indicates the motion of the conductor. So we can indicate the motion of the conductor with respect to the flow of the current and the magnetic field. So here the next part of the chapter is about electromagnetic induction, or we also call that as EMI. So what is this electromagnetic induction? The phenomenon of generation of current in a coil when it is subjected to change in magnetic field is called as electromagnetic induction. It is given by Michael Faraday. The current what is generated, that is such a type of a current, we call that as a induced current. The current what we generate, that current is called as, current is current only, children, right? Like how we studied in life process, blood is blood only, oxygenated, deoxygenated, it is a blood only. So current is current only here, but a type of current which is generated when it undergoes constant change in the magnetic field. Such a current is called as a induced current. We actually don't study that in syllabus, but we also have Faraday's law of electromagnetic induction. There are two laws on Faraday's. Now basically what the law will tell us, we don't study, but basic information I can give you. Now how much current is generated? Question number 1. How can I increase the generation of electric current to a more level? Simple. If I use a smaller coil, and see basically how it works, if I have a coil and if I place a magnet in this, assume that this is a coil and I just place magnet in this, I attach a galvanometer. Galvanometer gives me how much current is generated. Along with that, I can also connect an ammeter, but I connected galvanometer because galvanometer gives me the current deflection, also the direction of current deflection. That is very important. Which direction the current is flowing, galvanometer will tell me. So if I just insert a bar magnet here, there is no deflection. But if I insert it again and again, if I insert it, put it out, insert it and put it out, there is continuously magnetic field generated, that is magnetic field is changed in the given circuit. So that is how induced current is produced. If I insert the magnet in a very fast motion, that means more and more current is generated. Point number 1. Point number 2. If I increase the number of turns, now simple children. Now see here, if this wire has 1 turn, 2 turn, magnetic field is created here, magnetic field is created here. Very small magnetic field. Suppose like this, if I have 10 turns, imagine magnetic field is multiplied 10 times. So more the number of turns, more the magnetic field created, more is the induced current generated, right? So Faraday's two laws tells us about how the induced current what is generated is based on what, which we do not study in your syllabus. There is an activity given in your book on this basis, on this basis. Now here when we insert a bar magnet in and out, so see I am inserting the north pole here and south pole this side, there is a type of deflection showing. If I just change the direction of south and north, the deflection again changes. This is an activity where we understand that induced current is generated. Here, now there are two coils here. Both the coils, now one coil is attached to a battery, another coil is attached to a galvanometer. Now, how to create magnetic field? If I bring a bar magnet and insert it inside continuously, magnetic field is created, and and only then the deflection is seen. Otherwise, nothing. How is the magnetic field created here in this conductor? This is our electromagnetic induction. So here coil 1 and coil 2 this is magnetic effect of electric current. This is electromagnetic induction. So there's an activity where we see both the things happening in one. How? Now this works on magnetic effect of electric current because I have connected this to a source. I have not closed the key still. How do I create a magnetic field here? I can create a magnetic field if I just pass the power supply, right? The minute I pass the current in the conductor, that creates a magnetic field. It is magnetized, right? The minute it is magnetized, this is also very near. So this effect of magnetism, whatever the field is created, that is also affected here also. At a stretch, for a second, this coil also behaves because there is a sudden change in the magnetic field, right? Because the magnetic field got created here. See, there are like vibrations coming, you think. Magnetic field created here, that vibration just went to this part also. There will be for a second, you can say, sudden deflection taking place here at once only, right? Because I just created. Now, for example, when I insert a magnet and take out, there is a magnetic field created. Galvanometer shows the deflection. Suppose if I keep the magnet there only, I don't bring it out. Is there any deflection? No. But the minute I insert and put it out, magnetic field is created. Similarly here, the minute the switch is on, magnetic field is like vibration switch, it moves. There is a magnetic field created. With that respect, current is induced, right? But will that continue? No, it will not continue again. For that, if I again switch it off and again switch it on, again the magnetic field is created, right? But that time the current is drawn in the opposite direction. Now, why that direction changed? What is the meaning of that direction? You study that in detail in 12th standard children. Here only understand what is this activity about. There are questions asked on this activity. Most of the time there are many questions. If you just randomly check the previous year question papers, sometimes there are activity based questions which is asked on this sometimes. So this is about electromagnetic induction. Now we understood that there is a current generated in the circuit. Now how the current is generated, that depends upon which direction is the conductor moving, right? So, for example, magnetic field, if I have two magnets here attached, so this is north and this is south, and this is the magnetic field, right, from north to south. I place a conductor here, okay. I place a conductor and I also know that the conductor is moving in which direction. Now I should know what is the flow of the current here. In which direction is the current flowing? How do I tell that? See, I have a conductor placed between the magnetic field, and when I move the conductor, that's what? I move the magnet or conductor, whatever it is, there is the induced current generated. That induced current is generated in which direction? How to identify that? That is given by Fleming's Fleming's right hand rule. Left hand rule, it gave the information about motion of conductor. Right hand rule, we know how the conductor is moving, we know the motion, we know the magnetic field, but we are not aware which direction the induced current is flowing. So that is given by Fleming's right hand rule. So let us see now what is Fleming's right hand rule. Fleming's right hand rule is also called as a generator rule. In the beginning itself we discussed the two things in the chapter what we are studying about: magnetic effect of electric current and EMI. Magnetic effect of electric current works on Fleming's left hand rule, on application is motor. Electromagnetic induction works on Fleming's right hand rule, application is generator, right? So when we talk about generator here, it is just in the textbook point of view, it is a general generator only. We do not study in detail about AC generator and DC generator. There is a difference, children. I'll make you all know that. I'll make you all understand that. First, let us understand Fleming's right hand rule. See, right hand thumb rule is different. That was given by Maxwell. Again, I am repeating. Holding a conductor in right hand and the fingers curl will give you magnetic field and the current. That's different. Fleming's right hand rule is, again, arrange your first three fingers of your right hand such that they are mutually perpendicular to each other, as we had done for the left hand, where, again, same thing. Forefinger represents magnetic field. Thumb finger, that is main finger, represents the motion of the conductor, and the center finger represents the induced current here. Okay. So mainly when we arrange our thumb finger, forefinger, and the center finger I will use. Why? Because center finger induced current I can use the word, where thumb indicates the motion of conductor, force on which, mechanical force also we can say. Forefinger indicates the magnetic field and center finger indicates the induced current. So if I know where is the conductor placed, how is it going to move, and magnetic field of lines are going from which direction, I can tell the direction of induced current generated in the conductor, right? With the help of right hand thumb rule. So application is generator. Fleming's right hand rule is also known as generator rule. What is generator rule? Explanation. Arrange your first three fingers. What is motor rule? Fleming's left hand rule, what you have to explain. Let's understand in detail about what is a generator, on what principle does its work, its construction and working. Let's understand that in detail. Electric generator. Electric generator is a device which converts mechanical energy to electrical energy. So that is, some work is done. That work converts that into a electrical energy. Now, simple thing, if you understand, how is the power generated in the power station, children? The water from the top falls on the turbine. The mechanical energy converts into kinetic energy. The water which falls on a turbine rotates and thus electricity is generated, right? So, how it actually generates. Now, when we talk about this generator, now this is not a generator which I and you use it at home. But our generator, inverter, what we call, also works on the same phenomena where it is stored in the form of a battery that gives us current whenever there is no power supply, right? But this main thing what we talk about, this is something how it works when we draw the power in the power station where the current is generated, right? That thing you should keep in mind. This is something not which works in mine in your home, this generator. We are not generating electric current, remember. We don't generate electric current. Where is this current electricity generated? In the power station. So this actually phenomena works there. That is how it works in a small manner we will understand. Principle, whenever a closed circuit, the magnetic field lines change in a closed circuit, right? The magnetic field lines change and induced current is produced. That is, it works on the principle of electromagnetic induction. So let's again have the same. Now see here, diagrammatically everything is same here. We have two magnets, then we have a coil, then we also have an axle or armature which is used to rotate it. It is connected to two rings, but the rings here used are slip rings. Now slip rings is one whole ring. Split ring is one ring which is actually cut into pieces. Split we used in motor. Slip rings we use in generator. Now again children, when we talk about AC generator, we use slip rings. DC generator, we use split rings. I know. Now you should first know what is AC and DC. You will understand that once we complete this process, right? But here we are studying about electric generator. Of course, it is AC generator only, but we don't mention it as AC generator because we are using slip rings here. Like this, there will be two slip rings in this. Since there are two slip rings located at different points, each slip ring is connected with the carbon brushes V1 and V2. And each brush is further connected to galvanometer. Now simple. Now ammeter we studied, voltmeter we studied, galvanometer we came across here. Ammeter is a device used to measure electric current. Simple, we know this already. Voltmeter is a device which is used to measure the voltage across, potential difference across the circuit. Galvanometer is a device which is also used to measure current. Then what is the difference between ammeter and galvanometer? Ammeter will only give me the current. See how will the ammeter box reading will be? So this will start from 0. So it will have those points, right? So this will either point at one point to me. This is ammeter. How galvanometer reading will be? Galvanometer reading will start from 0 here. So it will have reading this side, it will have reading this side. That means if the galvanometer is showing me towards the right, it is showing the positive deflection. If the galvanometer is showing towards the left, it is showing the negative deflection. See, it is not positive or negative current. It tells us the direction of electric current. In which direction is the electric current moving? Positive side or to the other side? Galvanometer is a device which is used to measure the direction of electric current. Ammeter is a device used to measure electric current. Here we want galvanometer only because I need to know main what here, direction of current I want to know. Which direction is the current flowing in the circuit is very important. Imagine you have drawn everything correct. Instead of this you put this. The whole thing becomes wrong because I have seen many a times children write the working principle, everything of generator and they correct a battery here, power supply here. Why you want a power supply when you are creating a power supply, right? So don't connect a power supply. Instead power supply, we connect the load. Sometimes they also connect a bulb. Why? With this direction it will show, the bulb will also glow, telling that current is generated. A proof, you can see the bulb glowing. Now a small setup what you will have in your school lab, what it is, a small, all the coils, everything will be there. You need to rotate it. Your armature has to be rotated. So once you rotate it, that means electromagnetic induction. Magnetic field is changing. Since magnetic field changes, you can see the bulb glow. Simple. But let us now understand with respect to magnetic field and motion of the conductor, how is the direction? That's very important. So, on what principle does it work? It works on the principle of electromagnetic induction, we know that, and on Fleming's right hand rule. So, arrange your three fingers of your right hand again, such a way that you know what is pointing the magnetic field and motion of the conductor. See, the motion is same, children, here. How did the conductor move? How did the conductor which was kept between this moved in the motor? It moved this side. Suppose, okay, let me show it. If this is the duster, okay, this is the conductor. How did it move there? It moved like this, right? This way. So from here, that means AB was pushed down. AB was pushed down means CD was pushed up, DC was pushed up, correct now? This was the direction it is moving. Let us understand it is moving like that only. That means it is moving in the downward direction. I know the direction of the motion of the conductor now. I also know the magnetic field. Let me apply right hand rule. So, right hand rule if I apply, it actually comes like this. Okay. So, this is motion of the conductor downwards. Now, which is this? This is my magnetic field, forefinger. Where is the center finger pointing actually, if you can see? The center finger is pointing down, right? So direction of current here, it is down. See here, this is my motion of the conductor. Motion of the conductor is moving down. This is my forefinger. So if I hold like this finger is actually showing downward direction. Induced current is moving in this direction. If induced current is moving in this direction, children, let us see. The current will flow from B to A, right? It will flow through the slip rings connected to the brushes, carbon brushes, in turn which is connected to the circuit, to the galvanometer, whence it will flow like this. From here, how it has to go? I will remove this bulb part. It has to go like this way. From here, it enters brush 2. From brush 2 to slip ring 2. Slip ring 2 to the second part of the coil, right? So, it actually goes then here. Let us see, is this correct or wrong? Okay. This conductor is moving up now. See here. If this is there, it is coming like this, means CD is coming on top. Let us see the motion of the conductor with respect to magnetic field, how the current position is done. Now, this is right hand rule when I talk about. So, this is motion of the conductor which is going on top, and this is about forefinger which is actually pointing towards this side. So here this is motion of the conductor, this is my magnetic field. Actually perpendicular when I have to talk about, this actually comes like this. This finger which shows, quite difficult to show here children, why? Because we can't twist and think. You can try this in your paper or book what you have. See, this is my motion of the conductor. Motion of the conductor, magnetic field, and the current which it is showing, it should be perpendicular to all, no? So if it is perpendicular, it should be like this. If you can see, I have just forced my finger here, right? It is showing upward direction. Is that correct? Fleming's right hand rule is working here. So with respect to Fleming's right hand rule, understand how is the motion of the conductor. If you understand the motion of the conductor, you also know the magnetic field where it is going from north to south. With respect to that, you can tell direction of the current. Now see here, nobody will ask you in the exam why you drew this or why or how you drew this, right? But it's very important if you draw this oval. For your understanding, I have given the rule here. This is how it works. So let us just see the construction and working. We'll just read that once. Similarly, like how I have sent you for the motor, I will also send you for a generator where you can actually see the working, how it is happening practically in a small animated video. Electric generator consists of a rectangular coil ABCD placed between the two poles of the permanent magnet. Two ends of the coil are connected to two rings R1 and R2. These are slip rings which I have mentioned here. These inner side of these rings are made insulated. The inner side of these rings are conducting to the two stationary brushes B1 and B2 kept pressed separately on rings R1 and R2. R2 has a separate one, R1 has a separate brush here. These two rings R1 and R2 are internally attached to an axle. Axle is to rotate. The axle may be mechanically rotated from outside the coil, inside the magnetic field, anything. Now we are doing it mechanically here, right? But there it does not happen like that. Axle rotation mechanically, they don't do it. How the axle will rotate? Probably when the water falls from a very height, the axle rotates, turbine rotates. It's happening. But here for a setup, we have to rotate the axis. The outer end of the two brushes are connected to the galvanometer again for direction to show the flow of the current in a given direction in the external circuit. See, the points I have given in each point wise, easy for you to remember as well as to write. When the axle attached to two rings is rotated such that arm AB move up and the arm CD moves down. Okay. Arm AD moves up and arm CD moves down in the magnetic field produced in a permanent magnet, At the half rotation, the CD starts moving up and AB starts moving down. See, one rotation when we talk about, it starts moving like this or it starts moving like this. It completely takes a turn. So once it takes a turn, it will take this path. Same children, same in motor what we did know, the same thing is happening. But the only thing here what will happen is current AC generator when we talk about alternating current. Alternating means what? Current is reversing at every half cycle. At one cycle this is the current, second half cycle the current changes. Something like this it goes. Current changes in one cycle the current is this, second cycle the current is this. Uncycle the current is this, second cycle the current is this. But when we talk about a DC generator, AC is alternating, DC is direct. Current is constant, that moves only in one. Simple. Now AC when we talk about, we have AC current in our house, right? Alternating current. Everybody uses alternating current only. DC current is a type of a current which is a stored current, like in batteries, dynamos and all what we talk, right? That is a stored current. Do we use that? Of course, we use that in the car batteries and all. That's different, right? AC current is a current which is flowing in mine and your home through the main board circuit, right? We'll also study that how the current comes to our house from which source and what all other points. Main thing is this, what you have to understand here. The current in the external circuit now flows from V1 to V2. Thus, every half rotation, the polarity of the current in the respective arm changes. That is why it is a AC generator. Now, here in the book, nowhere they have mentioned as AC generator. But remember, when a current changes its polarity, what is polarity? Now, we discussed there in the beginning, right? Plus, when you put the north to south magnet here, current direction is this side. When you change the magnet, current direction is this side. How do we know that? Because of galvanometer. Assume that in the first half, galvanometer is showing this deflection. Second half, galvanometer will change the deflection. Because at every cycle, there is a change in a reversing in a current, which is called as a alternating current. So, this is the working of electric generator. In other words, I can tell that as a AC generator. Suppose if you want for DC generator, children, there we use split rings. They will not ask you, since DC generator is not in your syllabus at all, not mentioned in your book at all. Even in your book, only the word generator is mentioned. And also the two things what you have to know here still is difference between alternating current and direct current. Alternative generator, AC generator and DC generator. So let's see few more points about AC and DC, about its advantages and disadvantages. So advantages of alternating current when we talk about, AC can be transmitted over long distance without much loss of energy. True, we get the transmission lines from main thing to a transformer, then to the board, then to our house. There is no much loss of energy. But the only disadvantage of AC is we cannot store AC. There is continuous transmission which is happening. You cannot store that. To overcome that, or what we can say is we have a DC current. DC current is a stored current, right? You can store that. Now, where it is stored? It is stored in the batteries, cells, storage cells, etc. We get a small dry cell. That is 5-volt battery, or the batteries what we use for our remote, or anything what we use for our watches. Those are all dry cells, nothing but a stored energy or stored current what we say, including the inverter what we use at our home, children, right? So that is something called as a stored current what we have, DC, through which we get the power supply whenever there is a power cut. Car batteries when we talk about, right? So those are all DC source. So loss of energy. Why DC can't be transmitted? Because loss of energy during transmission over long distance is very high. So it can't be transmitted. That is why we can store it and we can use that as a stored energy. What I can tell. So this was about alternating and direct current. and through which we also understood about motor, generator to different rules and on what principle they work. The last concept on this chapter, and since we are learning electric current or generation of this electric current a bit, let's learn about more or a bit in brief about domestic wiring. Now domestic wiring is something which is related to our house, how the wiring is done. But we are not going in very detail. We just touch briefly upon what is domestic wiring, what are the types, main three types of wires we use in domestic wiring. So this is something about domestic circuit which is present in our home. So we'll just touch briefly upon this. So when we see that there are basically three types of wires what we come in across, that is, one is earth wire, live wire and neutral wire. Three main wire which comes to our home for electricity supply. When we talk about a live wire, which is always in red color, neutral wire in black, earth wire in green. Now these colors what they are given is to identify which is a live wire. See, live wire when we talk about, it is also called as a phase wire, because you can say majority, the current flows is, this is the phase wire. That's always in red. Now tomorrow when you just see the circuit or somewhere at your home, red is always constant, children. Black, green, sometimes blue you see, but it's the constant color convention what we use, that is live is red, neutral is black, earth is green. Live wire when we talk about positive current which is flowing in that. Neutral wire when we talk about, it is black, absolute zero, negative, where no current flows. Earth wire when we talk about, it is grounded in green color. Now what do you mean by grounded? It is actually mounted on a copper plate or some metal sheet or something, burrowed, and it is digged deep inside the earth, right? Why it is done? Let's understand. So now basically when this wiring which will run through the electricity board fuse, thread to the electric meter, that is from pole to main supply, then to fuse, electricity meter to distribution box at our place, right? The main, now we have this socket. If you have seen, there are so many holes in the socket. Now have you ever observed when you connect your mobile charger, when you use your iron box, you use your refrigerator, washing machine, your PC, laptop, for all these things, what different types of plugs are required, right? We sometimes use only 2-pin, sometimes we use a 3-pin socket. Now this 3-pin socket when we talk about, there something earth wire comes into use. Now earth wire when we say that, as I have told, it is wounded on a copper metallic plate or something and then dig deep inside the earth. Now in the connection part, if you see, if you take a tester, please do not try this. When your electrician visits your home, you can just ask him this. So when you just check in one of the socket, it actually shows there is a presence of current. That is a phase wire, live phase. When you check in the another point, it does not show anything. That means there is no current which is flowing through that, and that is a neutral phase. There is one more point. See, only your heavy appliances will have a 3-pin, where the last main pin what we say is nothing but which is a earth wire which is connected. Now what happens if this earth wire is not done or earthing is not done properly? Sometimes if you have when you accidentally, sometimes you touch your refrigerator, you might have felt a slight electric shock or something sensation in that, or when you are plugging in your pen drive into your computer or something, you slightly feel that there is a flow of electric current. So what happens if earthing is not done is, electric current flows through our body, and it flows through our body and then to the ground if earthing is not done. If earthing is done, electric current which is actually passing will flow directly to the earth rather passing it through our body. Now the smaller part what we get the electric shock is bearable. So sometimes due to some leakage of current or any mishap happening, current which actually flows into our body can also lead to a death, right? So we need to be very careful with these things when we are handling. So now these wires, when they are connected to our home, there are chances sometimes of short circuiting, overloading, or if earthing is not done properly. Now what is this short circuiting? Now this earth wire and live wire which are there inside our all circuit boards, connections, everything, they are always going parallel. Parallel in the sense they are always going together, right? But accidental, there is an insulation for the wires, insulation for this wires also. By some chance, if the insulation gets worn out and live wire comes in contact with the neutral wire, there are chances of short circuiting. You might have seen many ads which are coming up based on wires, right? Use wire advertisement when they give, use polycap wires, so and so wires. Why? Because such good quality wires, according to them, will not give rise to short circuiting, because over the usage of these wires, sometimes they may worn out, that is outer insulation might worn out, and when they come in contact, that leads to a short circuiting part, right? That is something called as short circuiting. There are other chances sometimes called as overloading. Now overloading, when it will happen, you have a socket or a 3-pin or a 4-pin socket, multi-socket what you can say. Now each socket is designed in such a way that either it allows a 5 amps current or a 15 amps current. So in our home basically we have two types of lighting what we can say, or two types of flow of current which is used. One is lighting and another is for heavy appliances. Now for your light, fan, basic your TV and all, 5 amps current is more than sufficiently enough. But for your heavy appliances, 15 amps current is required. Now if you have a inverter or something, you will come to know this, you have a separate connection given to a 5 amps as well as 15 amps. Now suppose you have a 5 amp socket and where you have overloaded that with, for example, it is multi-socket. You have plugged in one for ironing, plugged in one for mobile charger, plugged in one for your TV, plugged in one for your set-top box, plugged in one for something else which is running. Simultaneously, 4 to 5 appliances are running together on a 5 amps, heavy appliances also. At that point of time, the name itself will tell you overloading. There is a overload on the current on the circuit, and that overloading might sometimes burst out the appliances or anything can happen. That might also lead to short circuiting and then to any other things. So these are the two basic things what you have to do. Third one is earthing, which we already discussed. Now in this domestic circuit, children, sometimes very rarely they ask you this figure, but if they ask you, you can just write, draw as it is. Main things what you have to know here in domestic circuit is 3 types of wires. See, we are not learning about about electric thing in detail. We should only know about 3 wires, that is live wire, neutral wire, earth wire, their colors. What is the main purpose of these 3 wires? Which are the 3 main safety devices what we have? Fuse is a safety device. Did we learn about fuse? Yes, we learned that in electricity chapter. What is a fuse? What happens? Fuse offers a low resistance or a high resistance. We understood that. Why? Because suppose if there is a huge amount of thing which is flowing inside, it will immediately stop, right? It will not allow more current to flow. It will stop and cut the circuit there. It is always connected in series with the given circuit so that it can cut off. So fuse is one safety device what we have at our home. See, where is this fuse connected? Pole, electric main pole to the main supply. Then we have a fuse. Then we have electricity meter, distribution box. We sometimes nowadays in the latest trend we also have MCB, miniature circuit breaker what we say. So in case anytime a high current which is flowing, the circuit automatically puts off, miniature circuit breaker, that is why we call that, so that any high current should not flow into our home. So one more important thing what you have to know here is the potential difference between live and neutral wire in India is 220 volt. Now sometimes what appliances we use here, we cannot use that appliances if we go to outer states. Because in India, basically, between live and neutral, the phase or the voltage what we have is 220 volt. That differs in other places. So overloading is what we understood. Causes of overloading also, it is accidental hike in the voltage or use then more than one or more appliances in a single socket. So it is not that you use your small lighting and a mobile charger, that's different. Using your heavy to heavy appliances in a single socket, that actually leads to a overloading. Then safety devices is electric fuse, earth wire and MCB, which is a miniature circuit breaker. You need to only know the definitions and meanings here, children. About fuse wire or about the fuse we have already studied in the previous chapter. It's the same repetition here. Then what does an electric short circuit occur? Some about the domestic electric circuit, certain question and answers type are given which you can just go through. What is an earth wire? Why it is necessary to earth the metallic appliances? It is necessary because otherwise the current will flow through our body and then go to earth where we get an electric shock. Now if you have a proper earthing, if you touch a refrigerator, there will be no slight what you can say electric shock from the refrigerator. You might have experienced this, right? That is only because there is no proper earthing at home. If in case earthing is proper, none of the devices gives the electric shock. Neither your refrigerator, neither your PC. Sometimes when you touch the CPU or when you try to plug in the pen drive in this, you feel the electric shock. It's only because of improper earthing. What is electric fuse? What is the importance of electric fuse? You can just go through this in the question answers given part. So again, in domestic circuit, you have to only understand a brief about these wires, not in depth, because we are not studying anything where we can become an electrician and start repairing our own things. You again have this in detail in your higher studies when you study that. So with that, we complete the chapter Magnetic Effect of Electric Current. So in the whole chapter, where we divided into two parts, Magnetic Effect of Electric Current, where when we pass current in a given conductor, magnetic field is generated. So application of that is motor, which works on the principle of magnetic effect of electric current, and the another rule what we apply there is Fleming's left hand rule. Then the second part was electromagnetic induction. That is, if there is a continuous change in the magnetic field, then the induced current is generated. So application of that is a generator. So the rule what we use there is Fleming's right hand rule. Apart from that, we also studied about right hand thumb rule, that is Maxwell's thumb rule, where you know the direction of current, you can tell how the magnetic lines are moving in a straight conductor, circular conductor. What is a solenoid we understood, and at the last we understood about domestic circuit. What is a circuit connection? Basically in our home, from where the current electricity flows, from pole, main supply, fuse, electricity meter to distribution box, types of wires, types of safety devices, and why are they useful.